Hello, this is Dr. Scott Dennstaedt, founder of EZWxBrief, your best online source for aviation weather and education. Welcome to episode 10 of EZWxChat, a program to discuss topics related to aviation weather. Well, in this episode, I'm going to talk a little bit about instability indices that you'll see on various different charts and forecasts, specifically looking at the Skew-T log P diagram. There's a lot to talk about, and I won't be able to cover all of it in just this particular episode. And certainly there are probably questions you might have even as I go through this, because it is pretty complex. Talking about a Skew-T diagram, a thermodynamic diagram, there's a lot of aspects of this diagram that most pilots certainly don't have a good grasp of, but nevertheless, there's some good useful information that you can process by looking at this if you know how to interpret it. And that's kind of the goal here today, is to give you at least some indication of what you can do and what you can't do with these particular stability indices. Now, I will say that for the most part, some of this is pretty easy to understand, and most pilots have a good foundation to start to learn this. But when you get into the nitty-gritty details, you may find that there are some, certainly some areas that you'll have to explore a little further with time. Now, first of all, let me just start out by saying that these indices that you see here on the diagram, including things like convective available potential energy, or the totals index, the K index, the lifted index, the Showalter index, the sweat index for severe weather, all those have well-defined limitations and issues that you certainly need to understand. I'm not going to be able to talk about all of these, and certainly I'm going to focus on one particular index that's probably going to be the best bang for your buck, and that is convective available potential energy. Now, we know that convection, essentially moist convection, especially when you get a pretty significant vertical development to it, we call that deep moist convection, is a result of many different, if you think about a recipe, of many different ingredients. That includes essentially instability, moisture, and a outside energy contribution component. If you are missing one of those three in sufficient quantity, usually you don't get deep moist convection. And I'm not saying thunderstorms, because we know that thunderstorms typically tell you that there's some kind of electrical activity, and we know that not all dangerous convection actually has lightning in it. So I like to think about deep moist convection. And so those ingredients again are instability, moisture, and essentially some kind of outside energy contribution. You may hear some people say lifting source, and I like to not use that, because that gives the impression that something is kind of shoving the air upwards from below, and that certainly does happen, but also you have other aspects of the atmosphere that allow air to rise. So, and I'll use this analogy, and we'll cover this analogy as well throughout this episode. But if you think about riding a bike, in order for you to ride a bike uphill, you have to actually put some energy into it. You have to pedal or have some kind of motor or have somebody push you from behind in order to climb that hill on a bike. Now, the other aspect of it too is, even if you're on a level surface, you still have to put some kind of energy into the system in order to move. So you have to pedal, or you have to have somebody push you, or it has to be motorized. So ultimately, in the end, there needs to be some kind of energy contribution somewhere outside of the bicycle itself per se. Now, if you're on a hill going down, all you have to do is hop on the bike, steady it up, and then you can coast without pedaling, without putting any outside energy. So I like to think of that as the different ways that that this deep moist convection can develop. Sometimes a significant amount of energy needs to be pushed into the system, and sometimes very little energy needs to be put into the system. But in most cases, some kind of outside energy contribution is necessary in order to get convection to start. And so I'm going to focus on these different stability indices to give you an idea of how to use them while you are using a Skew-T log P diagram like you see shown here. Now, the Skew-T diagram, and it depends on which one you're looking at. This is the one that's actually from ruxsoundings.noaa.gov. That's the one I used the most. You'll see on the right side there are a bunch of indices listed here, including the equilibrium level. That's the top of the buoyancy of any particular parcel, and we'll talk about parcel theory in just a bit. There's the level of free convection. That's the point you have to lift in order for essentially a bicycle to go down the hill without having any outside energy contribution. Call that the level of free convection. There's the lifted condensation level. And I mentioned the sweat index. And that's not sweating as in you're perspiring. This is called a severe weather index. And the Showalter index, lifted index, K index, total totals index, and convective inhibition, as well as CAPE. So all those are listed there for you to use. Now, each one of these has some kind of background that you have to understand. Again, I'm not going to focus on all of those particular indices. We just don't have enough time for this program, but I'm going to focus on the CAPE, convective available potential energy, as well as the K index and the lifted index. Now, with some of these indices, you actually have to lift a parcel of air. Essentially, the idea is that we want to play a what-if game. Let's lift this parcel of air up and see what happens to it. And if it continues to rise on its own, we know we have some instability in place. And that would be true for the convective available potential energy, which I call CAPE, and then the lifted index, and also the Showalter index. The lifted index would essentially be another index that you have to actually lift air up. Now the K index, as we'll discuss, doesn't have that specific parameter. So let's kind of start with the K index first and understand kind of what it's trying to tell us and what it's not trying to tell us. So I'll take and pull up a slide from one of my many workshops on EZWxBrief. This is one specifically dedicated to the K index. And I'll walk through that with you. And if you look at the advisory circular, it's been updated since then, but ultimately the K index is a measure of thunderstorm potential based on vertical temperature lapse rate, moisture content of the lower atmosphere, and vertical extent of the moist layer. That's a fair representation of this. I wouldn't necessarily say it's a measure of thunderstorm potential as much as it is a measure of convective potential. And in all honesty, it's not really a great convective potential forecast or indice. So we'll walk through that so you can understand. So the K index is one of those indices that you were kind of required to learn in your primary training. And that includes the understanding of how this plays into convective potential. So the K index is a pretty simple thing, and you notice there's nothing in here about any kind of parcel, because we're basically just looking at the atmosphere into itself to see what we see from that particular vertical profile. And so you can imagine taking the data from the surface all the way up to the top of the atmosphere and then pulling out specific points on that and doing some analysis. And so you'll see 4 different terms here. And the K index can actually is usually positive. It can be negative at times in really, really stable conditions or very dry conditions, but ultimately it's usually a positive number. And when that number starts to creep up to 37, 38, 39, 40, 41, 42, then you know you've got some conditions that are prime for deep convection to develop. And so you'll notice here, the first two terms here, this is the temperature at 850 millibars, which is roughly 5,000 feet. Subtract off the temperature at 500 millibars, which again is roughly about 18,000 feet. And that looks a lot like a lapse rate. So we're just taking two temperatures and subtracting them over a layer from 5,000 to 18,000 feet. And so again, that's just saying how much is the temperature changing over that particular spread of altitudes. And we know that most of the time the 500 millibar temperature is going to be much colder than 850. So this is always going to equate to a positive number. Now, since the higher the K-index gets, the more convective potential there is, we want to figure out how do you get higher and higher convective potential. Well, certainly a large lapse rate, which means you have a lot of instability, is one way to do that. The other way is to look at the second set of terms here, which you see is the dew point temperature at, again, 850 millibars or 5,000 feet about, and you subtract off that the temperature dew point depression, which is simply just the dew point spread, temperature dew point spread at 700 millibars or roughly 10,000 feet. And so you can see the word here is moisture. Moisture is really what this is capturing. So here's our instability parameter and here's our moisture parameter. And we're going to see that CAPE and lifted index are also similar to that in that they both show the possibility of instability and moisture. But none of these indices talk about that outside energy contribution. They're only a situation where they're looking at those two, instability and moisture. So in effect, they're not forecasting. You can have very high CAPE values, very high lifted or very negative lifted index values, as we'll see, or even very high K-index values, and have zero chance for any kind of deep moist convection or thunderstorms, because of the simple fact is that they don't necessarily capture every aspect of what's going on in the atmosphere. So next here we have the ability to kind of see that when we increase the dew point temperature at 850, we increase moisture. We know moisture is the fuel for convection. That's going to increase the K-index. And when we have a small temperature dew point spread at 700 millibars or 10,000 feet, that's going to contribute less because this is a subtraction. So therefore, small temperature dew point spreads, as 0 is the perfect number to have here. Again, that's going to kind of maximize the K-index. So when you have in some cases, have a very dry layer around 700 millibars, or even a dry layer at 850 millibars, the K-index is not going to be all that impressive. So that's why it's important to understand the limitations of this. And that's about all I'll say with the K-index per se, although usually when that K-index starts to get up around 40, 41, 42, if convection does develop, usually it will consist of very heavy rainfall, in some cases flooding rainfall. In fact, the Storm Prediction Center often will talk about the K-index in conjunction with heavy rainfall events, usually driven by deep moist convection. And sure enough, you see the K-index shown up here as KI 27, which means the K-index is 27 in that particular case. Now the next one I'm going to talk about is the lifted index. Now there actually are variants of the lifted index and also variants of the convective available potential energy. So that's where it gets very complex, and I don't want to get into all the details, but I want to show you that there are some differences that you need to know about, and you need to kind of understand which one you're using. Otherwise, it won't make a lot of sense what you end up seeing. In other words, you'll say, geez, Liz, there wasn't much. CAPE value was very, very low, maybe even 0, or the lifted index was positive, but yet we got this thunderstorm roll through. And what's going on with that? Well, in some cases, convection can develop what's called elevated convection, where the lifting or the air rising doesn't start at the surface but starts above. We usually see that around areas of warm fronts, or in some cases around where like a mesoscale convective system is moving over an area of fairly stable conditions. You can actually have a cold pool of air resting at the surface, and that mesoscale convective system rolls over that cold air, allows some air to rise in that situation, but in some cases the air is not starting from the surface per se. It may actually be starting the lifting, if you will, maybe starting from higher up, 5, 6, 7, 10,000 feet or so. In that case, looking at a surface-based parcel is not going to give you the right answer. So we'll look at the variance just briefly, and we'll talk about how CAPE and lifted index are calculated. So lifted index is one of those that you're probably required to learn in your primary training. And it turns out that most of that training focused a lot on the surface-based lifted index. And to create a surface-based lifted index, you basically have to lift a parcel starting at the surface. So I basically put my cursor right here on the surface where it intersects the lowest part of the Skew-T diagram. I click on it, and this particular sites, that's the rooksoundings.noaa.gov site, provides you with the magenta line here, which is the parcel's lapse rate. In order to find the lifted index, all you have to do is find the 500 millibar level, which you can see right here, and all you want to do is subtract off the environmental temperature from the parcel's temperature, and that will give you the lifted index. So in this particular case, it's about minus 8.5 for the temperature that you can see there, and the parcel is let's say around, we'll just keep it simple, around 0 degrees Celsius. So that's about a minus 8 or so lifted index. It might actually be a little bit like a minus 1 or so, but ultimately it determined that the lifted index here was minus 7, whereas we were looking at this as probably being somewhere around minus 8 or so. Well, again, this is because of what these indices are relating to, and I'll talk about that in just a bit. So that's all you have to do, is you lift the parcel up and you do subtraction of the environmental temperature, whatever that happens to be, and subtract off the parcel temperature at that same level, altitude, in this case 500 millibars, and that's your particular lifted index at that particular point in time. So it's based on 500 millibars. Again, 500 millibars is roughly half of the weight of the atmosphere is above 500, and half of the weight of the atmosphere is below 500. So that's again kind of why they chose the 500 millibar levels, because it's kind of the midpoint in the atmosphere per se in terms of overall weight. But you'll notice if you look at the temperature differences between the temperature and the parcel temperature at higher altitudes, you may even see a larger negative number per se. So essentially, the further the magenta line, that parcel lapse rate, is from the actual temperature, and this comes from a analysis, which is the model's initial conditions. Essentially, you think about this. This is basically just doing a simple subtraction problem. You may find that at higher altitudes, the number may be even more negative. So this is why, unfortunately, when you start playing around with this, you'll notice that if for some reason the temperature kind of takes a little hard right turn and pinches right there kind of at the 500 millibar level and then kind of juts to the left after that, you may see that the lifted index may be -1 or 0 in some cases, but yet you're going to see that in those situations you can still have a lot of convective potential that's kind of hidden, because that lifted index again is based at 500 millibars. So let's look at another sounding, a little bit different. You can see this one here is doesn't look the same. It doesn't look like it has a whole lot of anything going on here in terms of instability per se, but there actually is, and it's showing here the lifted index is a +4. And that means typically you think, well, that's a stable atmosphere. For the most part, it pretty much is. So if I click on the surface here, what you'll notice is that the parcel lapse rate here, that magenta line, is all to the left of the temperature, and that means that you have a essentially a stable environment from that standpoint, from that particular parcel. And you can go to 500 millibars once again and do the math, and you'll notice that it'll come out to -10 minus a -9, so you'll end up with a positive number here. In this case, they're calculating to be +4 based on whatever parcel was lifted to produce that number. So positive lifted indices are generally saying that you have fairly stable conditions. But you notice I lifted this from the surface. And I'll talk about that when we get to CAPE, which is next. So ultimately, it depends on how the environment is poised, set up, and ultimately it'll depend on what parcel you lift to understand what's going on from that standpoint. So let's go back to the other sounding here out of Indianapolis, and this is a sounding analysis. And we lifted this surface-based parcel. But what happens essentially is that this number up here that you see, 4,010, and it's called joules per kilogram. Joules is an energy unit. So it's essentially, and CAPE can never be negative, it always has to be positive, is simply the area of this between these two curves. So we have the temperature line in red and we have the magenta line here, and if you create and do essentially, if you remember from your days of taking calculus, if you took calculus, if you were to integrate the area under a curve, that's essentially looking at what CAPE is all about. It's basically creating and understanding the area, how much area is between the parcel and the temperature line. And when the parcel is to the right, it'll be a positive CAPE value, as it is here, and you're creating an area. So ultimately, it's the size of this area that is being captured, not just at one particular level like 500 millibars. It's actually calculating, essentially, if you think about it, if you take every possible lifted index, looking all the way up through here and kind of adding them all up, that's not the way it works, but it's kind of what it's doing. It's kind of taking advantage of understanding all possible lifted indices, and then at that point in time, that creates the essential area between those two lines. That gives you the area, or in this case, how much energy is available for convection. You can think of, we know the difference between kinetic energy and potential energy. So this is just potential energy. It's like if you took a spring and you collapsed it with your hand, you're turning kinetic energy into potential energy. As long as you hold your hand over that spring is not going anywhere. It's going to sit there until you let go of it, and then it can release its potential energy into kinetic energy. That's essentially what we're kind of measuring here. The CAPE value just basically shows you how much compressed we are with the spring. And once the air rises to this point right here, where the parcel is always going to be essentially warmer than the environment, then that parcel can rise freely without having any outside energy contribution whatsoever. And that's where we come up with this level of free convection here. That level of free convection is in millibars. So in the case of 808 millibars is essentially where it's looking at where the level of free convection is located. So ultimately, that's where it's going to show, and that's right about here where this black line is located here. So in the end, this particular figure up here on the upper right under CAPE, we call best CAPE, or what's called most unstable CAPE. And so let's go back to the other sounding here where I basically lifted a parcel from the surface. But what happens if I lift the parcel a little bit higher? And I go up to a little bit higher than that, and I'm clicking on the temperature line, but at higher altitudes. I'm sampling it, saying, do I actually get, whoa, there you go. Now I get a little bit of CAPE in there because I lifted a parcel from a higher level. And I can essentially do that for each possible parcel. And now you see that the parcel, if I lifted it up here starting around, let's say 740 millibars, or roughly 8,800 feet, now that parcel does become a bit unstable at that point and can essentially allow for the rising air to occur. So this is what we call most unstable CAPE, meaning that you lift all possible parcels from the surface up to 300 millibars and see which one comes out to be having the best CAPE, or the most CAPE, highest CAPE value. And when you do that, you notice that this is probably creating the possibility of elevated convection. By no means is it anywhere near the amount of instability we show here with a CAPE value of 4,000, but ultimately there is still some instability showing up here at a CAPE value of 400. Again, this is the best CAPE, or the most unstable CAPE. There's also another one called a mean layer CAPE or mixed layer CAPE, where they average the first 100 millibars of temperature and dew point near the surface to produce the ML CAPE, as it's called. I'm not going to talk about that today, but ultimately this is the idea here, is that you can lift the surface-based parcel, but that may not be the only element here that you need to understand. So if I lift a parcel from a little higher altitude and thinking about that air rising over in a warm frontal scenario, tapping into some instability aloft, and sometimes it can be essentially very huge in terms of lifting it from a higher level. We see this a lot, and there has to be some kind of again, outside energy contribution to get this going, and we'll see that in certain synoptic weather situations where that can possibly happen. So we may have to essentially, instead of riding our bike starting at a specific point, we have to plop ourselves, kind of closer to the hill and go down from there. So that's what we're looking at here. Now, this is not a lot of CAPE showing here, but it's essentially showing that there is some instability in the atmosphere if the lifting or the rising motion of air starts at a much higher altitude. And certainly the case here, most likely you can do the same thing and lift the CAPE, or lift the parcel at all these different altitudes. I'm just clicking on the temperature line, and it will certainly provide that, but it looks like for the most part, if you click on the very, very bottom, that produces the highest level of CAPE at that point. So the most unstable parcel is the same thing as the surface-based parcel. And sometimes the mean layer parcel is also the same as well. So in the end, in really unstable situations where you have a lot of heating of the day that can create the energy necessary, and you have the dew points itself are pretty high near the surface, and usually we have what's called a well-mixed layer here, and you know that it's a well-mixed layer because you see like the inverted V with the dew point and the temperature lines occurring here. That inverted V tells me that for the most part we have a very well-mixed layer in the atmosphere near the surface, boundary layer that is, and ultimately the ability for that air is kind of, you can see that the dew point or the parcel lapse rate here kind of parallels the temperature, and so that's sort of like riding a bike, if you will, on an even surface. It's really not really unstable, so you've got to have something to come along to kick it up to this level here, the level of free convection, where it can begin to rise on its own. So you don't usually, just because you have some unstable conditions near the surface, doesn't necessarily mean that that's going to erupt into a thunderstorm per se. In some cases, you also have a little inversion here at the top of this mixed layer, and in that particular scenario, we generally call that kind of a loaded gun situation. That is, it's got some convective inhibition, which is holding back that ability, and sometimes that convective inhibition is strong enough that even with a lot of CAPE that you see here, you may not be able to get much in the way of vertical development because of that inversion or that convective inhibition going on. But in some cases, if that convective inhibition kind of starts to wear away very quickly, or there's enough of an outside energy contribution to get it going, it kind of pops like a loaded gun would be, and it develops very quickly, and you can have significant updrafts. So that's one of the other aspects of this, is that when we look at CAPE, essentially, CAPE can come in, in two different kind of flavors. We can have what's called thin, skinny CAPE, where that essentially the temperature and dew, or the parcel temperature and the temperature are really just kind of paralleling each other really close, but all the way through up to the top of the atmosphere. In other words, the lifted index is probably -1 or maybe -2 at its lowest, so we call that kind of thin CAPE. But when you have this really fat CAPE where the lifted index is highly negative, and there's you've got a lot of area here, That fat cape usually means that when weather does develop and you do get that kind of pop through that level of free convection, then these storms and these cells can develop very rapidly, usually 10, 20, 30 minutes, and you can get into a full-blown, 6,000 feet per minute. You can do the math yourself, that you can easily reach the tropopause, which is typically around 35 to 40, 45,000 feet, depending on where you're at in the northern hemisphere. But just again doing the math, it doesn't take that long, for a full-blown thunderstorm or deep convection to develop at that kind of a rate. So thin cape generally means that those storms will develop kind of slower or gradually, and then the really thick cape, the fat cape, will mean essentially that you'll be able to see those kind of blossom up. So in cases, I usually look at this and I'll say, wow, this is pretty significant. So if I start seeing some towering cumulus start to develop, most likely that's when the trigger is pulled, and we're going to see these cells develop really rapidly, and that's the time maybe I can land and wait this out. If it was more thin cape, I can probably work my way through some of this stuff as well to get an understanding of how to make sure that I'm not going to be in a situation where I get caught on top of this thing and it kind of all develops around me, or I get kind of pinned in between several cells. So I can gauge what's going to happen and how rapidly these cells are going to develop based on whether it's a thin kind of cape or a thicker cape. So the last thing I want to talk about is what's essentially called the equilibrium level up here. That's where you see that the partial lapse rate crosses back over into the temperature line right here, and that's usually essentially the equilibrium level. Think about if you took a cork and put it at the bottom of a pool, it would rise up to the surface of the pool and stop, and essentially the same thing, the air will rise up to the equilibrium level, and generally it does have momentum at 6,000 feet per minute. It's going to overshoot that top, no different than if you put a ping pong ball in. It's going to kind of pop up on top of that water surface and kind of bob up and down, and that's really what happens in the atmosphere. The air rises through the equilibrium level because it has momentum, and it will be what we call overshooting tops in those areas, and that's where you have the most severe updrafts occurring in a convective cell or in a thunderstorm. And so now we know the tops here are roughly somewhere around 45,000 feet or so, but probably some tops may actually be much higher due to that momentum. So we can be looking at the possibility of maybe 50,000 foot tops with this kind of a weather system. So this is a pretty deep weather system that can develop if, and I'll say it again, if that you can overcome any kind of convective inhibition because again, if there's no outside energy contribution available, this may not develop into much more than a few white puffy clouds. And certainly there are cases where even having a very little bit of cape, like we see here, can also aid, especially if there's a potentially large area of weather where you can actually develop that lift or that outside energy contribution going on there. So I think that will give you a pretty good overview of the different indices, talking about the K index, where you don't lift a parcel, you're just looking at very well-defined points along this graph, the determinant index, and you can see here the K index is up there at 34. That's pretty high, but it's not certainly way high up there. And then even here, you look at where there's a lot more instability, and the K index is essentially 27. So, again, you can see the difference here that you've got some dry conditions here at 10,000 feet going on. So again, that's going to lessen the K index, kind of take it down a notch or two. Whereas when you look at 10,000 feet here, the temperature and dew point are pretty darn close together. In fact, they're touching. So, and you got a high, fairly high temperature or dew point temperature at 850 millibars. So you expect the K index to be a little bit higher in this case. So if there were some areas of weather, some rain that occurred, it would probably be a little bit on the heavy side in that case. And we talked about lifted index, essentially being able to show you it's just to find the 500 millibar level, and it's the environmental temperature at that level minus the parcel temperature, which is the magenta line. Simple subtraction problem. It's in degrees Celsius. So essentially that's how you calculate the lifted index. And when it's negative, it means essentially you have instability. Then you have CAPE, which is this area between those two curves that defined the potential for instability and moisture. And you can play around with this. If you, let's say, took this surface-based parcel and you took the dew point temperature and moved it further to the left, it would take essentially a lot more energy to essentially, because it's got a lot less moisture, you're going to need to lift it to a much higher level to start that saturation process. So the higher the dew point temperatures, typically the more energy, because we know as the air rises, expands and cools, it condenses out, and essentially it releases heat, and that release of heat is essentially what turns this magenta line to the to the right and follows along the moist adiabatic lapse rate. So moisture is really important, and essentially the more moisture at the surface, the quicker that parcel is going to saturate, and then the more condensation that's going to occur in creating that heat. So we have essentially the ability for air to evaporate, and then we have the condensation portion of it. So it's the latent heat that gets generated in that process that is used for, that is kind of the fuel essentially for convection. So that completes episode 10 of Easy Weather Chat. My name is Dr. Scott Dennstaedt, and as always, enjoy the simplicity of EZWxBrief.